We learn early that our innovations are only as strong as the foundations they are built on. Build them with strong support, and they will soar. Engineering innovations are no different. Without a strong foundation, successfully developing and deploying them will only get harder. Because as design complexity continues to rise, and time to market cycles shrink, siloed design and test workflows will be pushed to their limit. Today's enterprises are striving for digital transformation, striving to develop and deploy technologies at market speed, striving to improve execution within and across development teams, striving to make agile, well-informed strategic business decisions. As a company with deep roots in engineering, at Keysight, we understand. It's why we've created the pathwave platform, a complete data sharing and solution building platform that enables agile, integrated design and test workflows, no matter how large or small your enterprise. The pathwave platform is the strong foundation you need to master your next innovation. It streamlines your development process, speeds your time to deployment, and gives you insights to make better, faster decisions. Are you ready to accelerate digital transformation in your engineering enterprise? Contact Keysight to learn more about the pathwave platform today. Discover the strongest foundation to help your business soar.
Hello, and welcome to today's webinar. My name's Colin Warwick, and I manage the Pathwave Design Power Electronics here at Keysight Technologies. Today's webinar will cover how to reduce EMI in switch mode power supplies with post-layout simulation.
We'll cover three topics. The first topic is how higher speed SMPS switch mode power supplies results in a smaller, lighter and cheaper unit. But these higher speeds introduce new challenges such as unwanted EMI. The second topic will be suppression of EMI by traditional solvency workflow is costly, time-consuming and non-deterministic. We'll show how that's the case. Third topic, and the main topic today, that represents a new workflow, namely it's a series of virtual prototypes using post-layout simulation. And we'll show how this is cost-effective, how it's faster, and it yields deeper insights to suppress the EMI challenges that we all face.
Let's first look at the trends in the switched mode power supply industry that's driving the need for this. Consumers are demanding a lower cost, smaller size and lighter weight. And that's driving the industry to higher edge speeds, higher switching speed. We'll call this the high DIDT era, which is the current slew rate in the switch loop. Turns out if you go to these higher switching rates, you can make the heatsink, inductor and capacitor smaller, and that gives you the lower cost, smaller size and lighter weight you need. But the issue is that traditional kind of cut and try design methodologies don't work well in the high DIDT era, and the reason is that the high DIDT interacts with the layout parasitics in the circuit boards and gives you voltage spikes, which give you obviously internal problems, but also external conducted EMI problems. And in addition, the radiation from a dipole of length L is proportional to DIDT. And so that means that the radiation gets worse when you have the high-speed edges. So in this webinar, we'll be talking about the need to add a field solver into the traditional design flow to extract the layout parasitics into an EM-based model and enable you to deal with these two issues in an effective way so you can get the benefits of high DIDT without the deleterious voltage spikes and EMI problems. So as I mentioned, we want to make the switch mode power supply smaller, lighter and cheaper. Let's first look at these two big components, the inductor and the capacitor. How can we make those smaller? A switch mode power supply is basically a trapezoidal waveform generated by some kind of switch, and it smooths out to DC. The DC component is extracted using this LC low-pass filter with a knee frequency which is inversely proportional to the square root of the product of the L and the C. So if we want to make L and C smaller, the knee frequency is going to go up. So we need to switch faster in order that the DC component goes through and the high-frequency components are eliminated. So that's a fairly easy thing. We just need to switch faster. But if all we do is switch faster, some bad things can happen. Let's take this curve on the On the left here, this is the low frequency switching with slow edges, and the switching loss is 3.5%, these two small glitches that occur as the transistors go from hard on to hard off. So that's an acceptable switching loss probably. But if you just go to higher frequency and keep the same slow edges, now the switching loss increases to an unacceptable level. It's 15.3% in the case of the middle graph. That's obviously unacceptable. The reason why this occurs is now because the switching time is such a big proportion of the switching period. The transistors are spending way too much time in that dangerous area between on and off where they dissipate power, and so you get this switching loss. So to go to a higher frequency and get that benefit of a small L and a small C, you also have to go to a faster edge to get the switching loss down. If you want to make a smaller heat sink, you want to reduce the switching losses. So you want to reduce the switching losses, you have to improve the edge speed even more dramatically than improving the switching speed. And this is what gives rise to this high DIDT. The high-speed edges is what gives rise to a lot of the EMI problems. If you consider a trapezoidal wave, you have the fundamental switching frequency, which might be fairly low, but with sharp edges you get lots of harmonics. Just looking at the Fourier transform, and a trapezoidal wave has a minus 20 dB per decade roll-off, just the reciprocal of these Fourier components, which is the fundamental, and then a third is the third harmonic, a fifth of the fifth harmonic, and so on. That 1 over F dependency gives you a minus 20 dB per decade roll-off until you hit the knee frequency, which is the point at which the energy is 6 dB below the minus 20 dB per decade roll-off. The knee frequency isn't related to the switching frequency, it's related to the edge speed. A rule of thumb is you take 0.48 or some number close to 1 and divide by the rise time, the DIDT rise time. In this case is 20 to 80% rise time, and that will give you the knee frequency. This 0.48 number may vary according to the shape of the edge, whether it's Gaussian or whatever, but roughly speaking, the highest frequency you're emitting at is 1 over the rise time. Now, when you have frequency components in your switch loop in the tens of megahertz or 100 megahertz in that last case, you run up against not just the physics of emission, but also the politics. This is regulated. These frequencies are broadcast bands, and so all governments, depending on the region, have specific and stringent regulations as to how much you can emit into these communication and broadcast bands. So you have to be concerned with regulatory bodies and so on. So in general, each region and industry has its own very thick EMI text that says what to measure, how to measure it, and what passes and what fails. And these are not optional things. You can't ship your product until you've got compliance with the particular standard which you have to obey. So let's look at the traditional design flow from the low-speed era and see how that would work in a kind of high-speed era. The kind of cut-and-try approach is you do some pre-layout simulation, some kind of SPICE simulator, and you'll get the best case performance for voltage spikes and maybe for at least differential mode conducted EMI, but very little insight about common mode EMI because the layout isn't in there, and nothing at all about radiated EMI. So you build a prototype, maybe it's got some excess ringing, you can do some spinning, maybe 1 to 2 spins. These spins can be fairly expensive depending on the prototyping cost, and they also cause a big schedule slip. But in the low speed era, this is kind of an acceptable flow, and eventually you can beat down all the imperfections and come something that's very clean signals that pass the EMI spec. There isn't much radiation into the broadcast bands. Now let's look what happens if we try to apply this old methodology to the high-speed era. The number of spins goes up because the complication is much higher at high speed, and you're paying 3K a day in the chamber fees to get compliance. This is very unsatisfactory workflow in the high-speed era. So the core idea of this webinar is to present a new approach for the high-speed era. This is some customer we work with. This is actually ST Microelectronics case study that we published a while back. And begin the same way with some pre-layout simulations, but then we add a step post-layout simulation using an integrated EM circuit co-simulation. We have a virtual prototype. It's a white box. We can probe anywhere, do data displays, 3D visualization, and very quickly we can spin the design and get the best case approaching. This is the best case for internal voltage spikes, best case for conducted EMI, best case for radiated EMI. And so when we build the first prototype, we find it's pretty close to the ideal case, and we go into the chamber confident that we get first pass success. A unique thing about our approach to post-layout simulation is that we not only tell you there's a problem, we can get a very good, accurate prediction of, say, voltage spikes in a switch mode power supply. Here's a comparison of the simulation in ADS versus the measured data. Get a very good correlation on the voltage spike height and frequency. But unlike other tools, we have a special mode called circuit excitation. We replay the waveforms back into the EM simulation and give you a visualization of the current density on the circuit board. And this gives you some pointers as to where you need to fix the problem. We can pinpoint current crowding. Current crowding is a cause of voltage spikes because of inductance, and of course conducted EMI and radiated EMI as well. So once you see these red hot spots, you know that you have to thicken these traces or add some ground planes or whatever it is you need to fix the problem. It points you to pinpoints the root cause. It's quite a unique capability. We call this circuit excitation. Another insight we can get from simulation, which is hard to do on a lab bench, is the separation of differential and common mode noise. The definition showing here, you've got two rails. The common mode noise is the component where the two rails are going in synchrony, and the differential is when they're asynchronous, 180 degrees out of phase. And the important thing about differential and common mode noise is a very, very good and powerful diagnostic to fix the problem. In general, common mode noise is caused by a non-ideal ground coupling path, whereas differential noise is kind of internal circuitry. And they have different frequency characteristics and different causes. So if you can analyze the two components of the total noise, you get some clues as to where to go in and fix the problem. So here's an example. On the top right is the total noise. This is probably what you get from a chamber. But in simulation, we can easily decompose it into the left and center graph in blue and green. We've decomposed the total noise into differential noise on the left and common mode noise in the center. You can see that the differential noise is dominated by the switching frequency. And you can see that also in the time domain trace, bottom right here, the blue trace shows this kind of periodic switching frequency waveform. And in contrast, the common mode noise is mainly high frequency. It's kind of differentiated by the capacitance to ground. And you see that the bulk of the energy in the total noise in the high frequency, which is where you are most concerned about, that's where the mask is generally tightest, that's where the broadcast bands are. Most of that noise is actually coming from the common mode noise. And you can see that in the time domain and the frequency domain that we display in our simulation. And that's very important because then you know you need to fix the layout, because common mode noise almost always comes from layout problems. It's a poor return path and so on. That's easy to fix in layout. And you can see that by decomposing the noise and iterating on the layout and seeing how that affects the common mode noise, particularly in these high frequency bands. Now, an essential part of doing this post-layout analysis, obviously, is to have an EM field solver to extract the layout parasitics from the PCB and calculate the far field pattern. In the past, that was quite difficult to do because EM field solvers were very general purpose. They had a lot of settings, complicated to use, and they weren't really application specific. So what we've done is launch a new product, PE Pro, which is an application specific EM-based field solver It has a lot of this complexity already done for you. We have not only the field solver set up is simplified, we have test benches that mimic an EMI chamber, specialized data displays that compares the EM to a mask, and all around it makes it very simple because this is an application-specific product specifically designed for switch mode power supplies and answering these questions about conducted and radiated EMI. So here's an example of how I made this easy for you. This is actually a CISPA25 conducted EMI test bench, which is included with PE Pro. We place a post layout model of your electronics under test, so this is the lumped elements and the extracted PCB, and wire that into a test bench just like you'd wire in the actual product on a test bench in a chamber. We modeled the Lisn components, we modeled the spectrum analyzer, and so on and so forth. This makes it very easy to get you a virtual prototype that's specific to doing a conducted EMI test. On that test bench we have a data display template, so when the simulation completes it automatically opens up a set of graphs that represent the emission spectrum versus a mask, and we can display the differential and calm mode separately if you want to. As I mentioned, it's very valuable diagnostic to have those separated out because it kind of points you to the way to fix any problems or mask violations that you might have. We have several built-in masks, and also you can customize it very easily just by putting value pairs in of the amplitude and frequency corresponding to the Y and X axis. Now, when you're measuring conducted emissions, there are many test set variables, and being part of an instrument company, we have a good understanding of how you do these measurements, and so we've taken that knowledge, that measurement science, and built it into PE Pro, so you don't have to worry about these test variables. They're all taken care of in the test benches and data displays. I'll give you a couple of examples of the built-in capability. The first is the Lisn line impedance stabilization network. This is specified in the standard. It has several purposes. It isolates the power source from the electronics under test to reduce noise coming from the mains into the spectrum analyzer. It provides a known impedance source for both the power source and the electronics under test. It also prevents noise leaking back into the mains from the switch mode power supply. And very importantly, it provides a standardized tap point for the spectrum analyzer that's going to do the measurements that you need to have in order to get compliance with the mask. So this is the virtual Lisn that we provide as part of that test bench. It's built to a specific standard. It acts as kind of a low-pass filter. And it also provides this tap point here, be measured, where we hook up a virtual spectrum analyzer and as well as the power supply and the electronics under test. And that gives you this Lisn-like capability, a virtual Lisn and a virtual tap point for the spectrum analyzer. Now, all of these EMI standards are written around a spectrum analyzer, which is basically a super heterodyne receiver. You have an RF amplifier and a local oscillator, and it's a swept measurement. You mix the local oscillator with the incoming RF, and it passes through an IF filter, which is a fixed frequency filter. It has a fixed center frequency and a fixed bandwidth, called the resolution bandwidth. And that goes into an IF amplifier and a demodulator, and that's actually what gives you the amplitude as you sweep this measurement across the measurement band. And the standard specifies what the measurement range should be, what the bandwidth should be. So we have to mimic this in the simulation, because if you just do a naive FFT on a time domain waveform, you'll end up with what's effectively a 0 Hertz resolution bandwidth, and so you can't compare that with the standard or with the real-world measurement. So what we do is take that tap point on the Lisn and do some post-processing, some signal processing, and so that what we plot is what you'd see on a spectrum analyzer of the specific resolution bandwidth that the standard is asking for. Another thing that PE Pro takes care of is the detection methods. When you have this demodulated output, the standard will specify what you have to do with it. Typically, this is a time-varying waveform, because of internal disturbances in the electrodes under test. And so the detector response isn't a DC value for a given frequency. So you end up having to process that to come up with some specific number. And there's three ways of doing that. You need to just take the average value. So let's say that the black line here is the detector response. You can average that and get the orange value on the top curve. Another thing that the standard may specify is the peak value. It's kind of a snapshot. There's some time varying effect in the detector response, and the standard says that the spectrum analyzer must give the peak value. The third option is called the Quasi-Peak Responses. It's more complicated. You take the black line from the raw detector response and put it through a fast rise, slow fall filter to give you kind of a weighted average. That's the blue line. And then you average the output of the detector response, the Quasi-Peak detector response, to get you the final orange value, the so-called Quasi-Peak value. So these are all specified in the standard, and we take care of these for you in PE Pro using post-simulation analysis in the data display. So let's say you build your first virtual prototype and it doesn't pass the mask. What can you do about that? There's two main approaches. One is filtering, and the other is changing the layout. Let's talk about filtering first. This is kind of the least desirable option. For differential mode EMI, you can add L filters, T filters, pi filters, and so on, like on the left. For common mode, you want to have a set of capacitors that are connected to a good grounding point, the best return path you can get, and that will reduce the common mode EMI. The difficulties with these methods are twofold. One is that the components are not ideal. An inductor always has a series resistance and a parallel capacitance. A capacitor has a series inductance, series resistance. Transformers are not perfect. They have cutoff frequencies at the low and high end. And so if you're going to go the route of adding EMI filters, you have to allow for the fact that the components are not ideal, and the filtering is never quite as good as you'd like it to be because of the non-ideality of an inductor becomes capacitive beyond its self-resonant frequency, and a capacitor becomes inductive beyond its self-resonant frequency. So you never quite get the benefit you'd like to have when you're adding EMI filters because of these real-world limitations of the components you can buy at a reasonable cost. Here's another example of a non-ideal component. One good way of fixing common mode EMI is to add a common mode choke. It kind of cancels out by adding antiphase component to the common mode emission. It's very simple to implement. The problem is that transformers don't work very well at low frequencies, nor do they work at very high frequencies. So the impact of these fairly expensive devices can be not quite good enough, especially in the high frequency regime where you have broadcast band and a tight spec. These non-idealities in a common mode choke cause the effectiveness to be not as good as you'd like. So if EMI filters aren't the way to get rid of EMI, what's a better way? And we believe there is a better way, and that is to use an EM-based simulator to look at the layout and improve it. Now, if you've only done pre-layout circuit simulation in the past, one of the biggest conceptual difficulty you have to overcome in order to do post-layout simulation is what we call the ground myth. Ruth Archambault always says ground is a place where potatoes and carrots thrive. It's not something that engineers should think about. We should think about return paths and just forget the whole concept of ground that you can get away with when you do pre-layout simulation. In pre-layout, you don't have to worry about return path. You can sprinkle ground symbols anywhere you like. But in post-layout, you should forget about ground. Only have one ground symbol. Don't place multiple ground symbols. Current flows in loops. So instead of thinking about ground, think about the return path. You can allow yourself one and only one kind of chassis ground symbol at the point that makes most sense. Usually it's the ground reference to the input power port, but it can be anywhere. Just make sure you only have one and only one ground symbol. And then in the substrate editor, use a conceptual, what we call a cover layer. as the chassis ground reference for the EMI extraction. This is conceptually connected to this chassis ground, and it makes the simulation results reference to a plane, a conceptual plane, which is 0 volts for all time and all x and y. So in this way you can account for return paths, and the return paths are what's going to give you most of the car mode noise. So you really have to model them. You can't ignore them like you do in pre-layout. Otherwise you'll get misleading results. So once we've set up our post-layout simulation, we found we're having some issues with voltage spikes or EMI. What can we do about it? Well, one thing you do is to take a non-optimized trace. This is the top red trace here. It's kind of skinny trace, and apply the techniques that have been applied in RF microwave for many, many years. Make the trace fatter. That will make it more capacitive and less inductive. Bring in a ground underneath the trace. Again, that makes it more capacitive, less inductive. You can even do bring vias up from the ground and put coplanar waveguide structure. Put a ground metal either side of the trace. And again, this will make the trace more capacitive, less inductive, and cause less emissions. So there's many, many things you can do in layout to reduce all of these effects. And they have much more advantage over EMI filters because they cost almost nothing, and they don't suffer from the fact that lumped elements have their own imperfections and their own parasitics. You're actually using the parasitics of the PCB in your favor to increase capacitance and reduce inductance in this case. So besides thickening a trace that has advantages of reducing the IR drop and the parasitic inductance, as in the top row, the middle trace is to think about the topology, reduce the return loops via geometry by shortening the loops, bringing the current loop into a more compact form. And the other thing you can do is to add low Esl capacitors. If you have a bulk capacitor here, on the left at the bottom, you can add a low Esl capacitor very close to the switching device, and that will add some filtering. So you can place the filtering components judiciously and in a way that's commensurate with the actual layout and the current return path. Experimenting with all of these in a virtual prototype is very easy compared to building real-world prototypes, because you can spin the idea in an hour or two, and you get much more insight from all of the virtual probing that you can do. So in summary, for conducted EMI, if you start off with a bad layout and no EMI filters, you may have some bad emissions. There are two routes you can go from this point. The non-recommended route is to just live with the bad layout, put on some large EMI filters, and this red square, you can see you end up with very poor efficiency, because the EMI filters are not only not perfect, they also tend to have resistance, and so they can be dissipative and give you poor efficiency. And you end up with a big bill of materials. A good example of this red square on the left is snubbers, which are RC filters. They dissipate half CV squared on every switching cycle. And they can reduce EMI, but they end up giving you poor efficiency. A much better approach is to go with this green square here, green rectangle. You first improve the layout using the EMI, the EM-based post-layout analysis. Then you may end up adding some small EMI filters to get the last dB of noise out of it. But that's okay, because you'll end up with a good efficiency and a smaller bill of materials, because you've added only a small number of EMI filters just to get that last dB of tolerance. A case study or a success story that we've had in this area is a joint paper we wrote with Rome Semiconductor, published in ICEP in 2016. Got a very good correlation on EMI, conducted EMI, using the techniques we've described here. So we talked about conducted EMI. Let's now move on to radiated EMI. It's a similar story, except now the spectrum analyzer is kind of connected to the EUT, not with a physical connection, like the Lisn we talked about earlier, but with a free space radiation going to an antenna, and amplify it into the spectrum analyzer. So radiated EMI typically falls off as 1 over R, at least is first order, and it can be reduced by good layout or to last resort some EMI shielding. Now, just as we talked about in the conducted EMI where we're adding filters, one way to get rid of radiated EMI is just to add shields. They tend to be expensive, and so we wonder, is there a better way of getting rid of radiated EMI rather than adding expensive shielding? And yes, again, improving the layout is the way we recommend, and the way to improve layout is to apply an EM field solver to extract the layout parasitics and its radiation pattern. So what's the relationship between layout and radiated EMI? Well, radiated EMI comes from unintentional antennae, and the printed circuit board is by far the largest source of these. There are two ways to generate EM radiation. The first is an oscillating electric dipole, the Hertzian dipole, and it's proportional to the separation of the two traces, L in this case, the current in the switch loop, which is your switching current in the switch mode power supply, I0 here, the impedance of free space, Z0, which is a fixed physical constant, 377 ohms roughly, the wavelength, which is specified in the standard, the radius, which is specified in the standard, typically 10 meters is the measurement radius that you measure radiated EMI from, and then sine theta is the worst case emission. In this case, the worst case for a dipole is when theta equals 90 degrees and sine theta equals 1. So if we plot that, we find that the emission is proportional to the frequency, because it's proportional to 1 over the wavelength, and the wavelength divided into speed of light is the frequency. And we can see that this is kind of a linear trace, and really the only thing we can do about this in the design is to make the gap between the two plus and minus rails as small as possible. All the other constants in this equation are things we can't control. For example, the R value we set by the standard, Z0 is a physical constant, I0 is the current we need in the switch loop to make the spec, and so on and so forth. So the L is the one we should focus on, make the gap between the two traces as small as possible. The other source of radiated EMI is another form of unintentional antenna called the oscillating magnetic dipole or loop antenna. This is when you have an oscillating current flowing in a loop. It creates a kind of electromagnet where the north and south is oscillating. And here the far field emission is a very similar equation to the previous one. Again, you've got the impedance of free space, the current in the switch loop, the theta worst case, which is again 90 degrees, sine theta equals 1, the R value, which is again specified in the standard. But now we have the loop area divided by lambda squared is the thing we have control over, or at least the area is the thing we have control over. Lambda squared is obviously the same as before, it's the frequency. C divided by the lambda is the frequency. But now we have a quadratic dependency for this magnetic dipole of electric field versus frequency. And the thing that we can do to get rid of the emission is to make the loop area as small as possible. That's really the only thing we have control over. Now these equations are all for one antenna, or one loop, or one dipole. What happens if you have more than one? If you have two, is it twice as bad? Well, not necessarily. Actually, if you have two, it can be a lot better. Now, it's kind of counterintuitive that two antennae might be have less emission than one. But the key to this is to use destructive interference. If you have two antennas that are in phase with constructive interference, yes, it'll be twice as bad. But if they're out of phase, the emissions cancel out. This is called destructive interference. And so two antennae can be actually have a lower emission than one. And it's quite easy to arrange antennas that are out of phase and have destructive interference. All you have to do is to split the return path, have a return signal return, and then automatically these two antennae are out of phase. They're opposite polarities, and their fields from these two antennas will cancel out. Similarly with the loop antenna, if you split the return path and have half the current flowing to the left of the signal, half to the right, Now these two loops have opposite polarities, on that kind of north-south there in antiphase, and again the two loop antennas will tend to cancel out. So a coplanar waveguide structure has a lot of benefits in terms of radiated emission because we get this anti-phase and destructive interference, and we can get a lot of the emission to cancel out just by organizing the layout. We don't need any shielding, just by some sensible layout and the use of destructive interference, we can make huge improvements to the radiated EMI and reduce radiated EMI very substantially at very low cost just by redesigning the layout. So in PE Pro, we make this very easy for you to do. We have a radiated EMI test bench. You put your device on the test bench, and then we have some specialized displays that let you see what's going on with respect to radiated EMI. The first specialized display is the far field emission pattern. In this particular switch mode power supply, the far field emission, this is actually at the switching frequency, is kind of a donut shape. The worst case is actually on this arrow here. And this is the point where this frequency, this particular switch mode power supply is radiating most strongly. So if you're doing this measurement in a chamber, you put the device on the test on a turntable and rotate the theta until you got the worst case. You'd alter the height of the antenna to get the phi, the worst case. But in simulation, we can pick this out for you very easily. We can give you a maximum emission plot. Here is the emission for the worst case theta and phi for each frequency point. So these blue dots represent the worst angle, the worst emission of that kind of donut pattern for a given frequency, and then the green line shows you where you are versus the mask for this particular radiated EMI standard. This is actually CISPA 22. So this is very convenient because you don't have to try and analyze that donut shape and find the worst case and plot it out by hand. We also make this for you and plot the worst case frequency point versus the mask. So our recipe for dealing with radiated EMI is similar to the conducted EMI. If you start off with a bad layout and no EMI shields, you might have bad emissions like in this rectangle in yellow here, and you have two paths to go. The non-recommended path is just to add a bunch of EMI shields. You may be able to fix the problem, but you'll end up with a big bill of materials, and that's not the best way of going forward. What we recommend is the route on the green route on the right, and that is to first improve the layout using those tricks I mentioned of destructive interference, use the EMI extraction, the far field emission pattern radiation, the worst case emission pattern plot. In that case, you'll reduce the radiated EMI very substantially at a very low cost just by altering the layout. And if you're still then in mass violation, then you may need to add some EMI filters, but a lot less than the case of the red rectangle on the left. So the benefit is then you'll end up with a much smaller bill of materials because you have to add less EMI filtering. Also, the EMI filters take up space and they add weight and so on. It's not desirable.
In this webinar, we're showing you how higher speed SMPS results in a smaller, lighter, cheaper unit. But the higher speeds introduce new challenges, such as unwanted EMI. We showed that suppression of EMI by a traditional solder and see workflow is costly, time-consuming, and non-deterministic. And the main topic was a new workflow that we presented, namely this series of virtual prototypes using post-layout simulation that's cost-effective, is faster, and it yields deeper insights to suppress EMI. So the next step is to request your free trial today at the URL at the bottom of this slide.
Now it's time for the question and answer session. Okay, Colin, here is your first question from Dong Sheng. What kind of EUT model is needed for the post-stem? Does typical layout tool output work with the EM post-stem?
Yeah, well, the way we do it is we model the electronics in the test as lumped elements, SPICE models, and we instantiate those components onto the printed circuit board by dragging and dropping the symbol for the lumped element onto its pads on the layout itself. We connect that way through ports. So we have a full model of the lumped elements, transistors, inductors, all the lumped elements are modeled as SPICE models and instantiated onto the board.
Great, thank you. And here's your next question from Aaron. Can I do both conducted and radiated EMI?
Yep, you can do both. To do the radiated EMI, you need a full wave solver. So in PE Pro, we have 3 solver modes. The RF mode of momentum, which is a quasi-static solver. It doesn't have radiation in it. It assumes that the propagation is instantaneous. Then we have 2 full wave solvers, momentum microwave mode and the FEM solver, and they both enable you to do radiated EMI, and you can do both conducted and radiated using either of those 2 full wave solvers.
Great, thank you. Here is your next question from Scott. If I don't want to use the CIS PR mask or other built-in mask, can I create a custom one? If so, how?
Yeah, that's very easy to do. There's a simple text file. You'd specify the list of value pairs, the y-axis limit, and the frequency on the x-axis. So make that very easy for you to do and create your own masks if you need to.
Great, and here's a question from Victor. Do you use .brd file from Layout Gerber files?
Yeah, we import Cadence's BRD format, and we import Gerber drill, and we also import ODB++ if you have Altium or Mentor tools. ODB++ is preferable over Gerber because you have Gerber's kind of dumb metal and one layer per one artwork per layer, whereas ODB++ has more smarts in it, and you can import more than one layer at once.
Great, thank you. And here's oh, sorry to interrupt you.
We support those formats. Sorry, just summarizing there. Go ahead. Yep.
Great, thanks. Here's so many questions. Here's your next question from Joel. How are the switching Mosfets modeled?
Again, all the lumped elements are modeled as SPICE models. So in the case of gallium nitride, we support the CMC's ASM model. In the case of silicon carbide, we support a proprietary PowerMOS model that can model silicon or silicon carbide MOSFETs. We also have a proprietary insulated gate bipolar transistor model, and we support all the standard SPICE models, PSIM, and so on.
Thank you. And here is a question, let's see, here's a question from Dominic. Is pathwave ADS just for radiated EMI? Will it work for non-Keysight LISNs and spectrum analyzers?
Yeah, pathwave is a broad initiative that covers the whole of Keysight, and it's open to third-party tools as well. So we could support a non-Keysight spectrum analyzer.
And here's a follow-up question. I have pathwave ADS 2020 with PE Pro in the Power Electronics bundle. I see the conducted EMI test bench, but not the radiated. Am I missing something?
Yeah, the radiated only came out very recently. You have to download the Update 1, ADS 2020, Pathwave ADS 2020 Update 1. It was released late last month, and it's available on Keysight.com. Use the ADS download page, and if you're on support, that's a free upgrade.
Yeah, and we also have a lot of links in our resources widget if you wanted to check those out as well. Here's a question from Steve. Does the simulation consider near-field effects?
Does the simulation consider near-field? It's a far-field measure, and for most of the radiated EMI standards I'm aware of, they're like 10 meters, and so the EOT is obviously a lot smaller than that. I think the answer is no, and it's not really necessary to have a near-field probe. It's far-field probe is what you need, and that's what we provide.
Great, thanks. And here's a question from Jerry. Do you account for EMI from the lumped elements like inductors or just the PCB?
Just the PCB, that's by far the dominant cause. If you need the lumped element emission, you can probably do that like pencil and paper. It's pretty trivial to do that, and I think you'll find that in almost every case, you're dominated by the PCB. They're by far the biggest pieces of metal in the system, and they carry the highest current, so they usually dominate. That's what we show in our plots.
And here's a question from Steve. Can components be modeled as well instead of treating as lumped elements? Shielded versus unshielded inductors, for example, are very different from their common lumped elements.
Yeah, we haven't come across that so far. I think you may have to use a 3D solver like EM Pro product to do inductors that are shielded. That's we have to think about that and get back to you by email. That's not a question we've had before.
And let's see, here is another question from Nissan. I'm designing a PCB base inductor and Rogowski coil. How accurately can I extract the inductance of the loop?
I think we need to think about that and get back to an email. I think that sounds like it's going to be a full 3D problem. A Rogowski coil is like a helical coil with a center tap. So I think you'd have to probably use a 3D solver for that. The PE Pro is mainly for laminar structures like trace and vias on PCBs and modules. But let's research that and get back to you.
Great, thanks. And here is your last question, Colin, from Steve. Does the simulation software solve for multiple layers or just a virtual ground?
Oh, it's multi-layers. Momentum can solve a large number of layers. Typically, these switched mode power supplies are between 2 and 8 layer boards. We can easily tackle that with Momentum or FEM. No problem.
Thank you for attending today's webinar brought to you by Keysight Technologies. Join us next month for the continuation of our Engineering Education webinar series, and enjoy your day.